Ladies and gentlemen, I think that we can start the last session of this workshop. We have two speakers. The first of them will be Professor G.B.H. Styan from McGill University in Montreal. Today I happened to hear a very interesting discussion between Dr. Styan and Dr. Olkin. The problem was when these gentlemen visited to Finland, made their first visit to Finland. And it appeared that Dr. Styan made the first visit to Finland in 1956, at a time when, for example, this university, this building didn't exist yet. But the decision to move the university from Helsinki to Tampere was made in 1955. After that year, I think that it was the year 1976 in January when George visited for the first time the University of Tampere. It took place in the academic year when he visited Professor Mäkeläinen's department at the University of Helsinki in 1975-76. Since that time, George has visited to our university so many times that I do not know how many times, but very many. He has been a key person in all of these conference meetings what we have held at the University of Tampere, and he has been a very important person to help in the arrangements, and he's really so important persons that it is difficult to overemphasize his role in these events. Dr. Styan will give a talk with the title More About Canonical Correlations in the Three-Way Layout. Professor Styan.
Thank you very, very much, Tarmo, for those very nice words. Il me fait un grand plaisir de remercier le workshop Secretary anonyme, mais qui, selon moi, n'est pas anonyme. I said those words in French, even though I do not yet live in the République indépendante du Québec, though I haven't heard any recent political news, so one doesn't really know. But I would like to take some time, and I promise the following speaker that I will finish before 5:30 so that he will not feel cheated upon. I would like to give tremendous heartfelt thanks to the very much non-anonymous workshop secretary, who is really two people, Simo Puntanen and Erkki Liski, without whom this conference would not have ever taken place. And in addition, the young ladies outside, Maria and Sirpa, who've also helped me in the first 3 weeks that I was staying here before this workshop began, I think also deserve a round of applause. We've had some discussions. I guess I was somewhat involved in the previous two meetings in Tampere, so we have been thinking about where we might run a second and third workshop that might possibly follow this. There have been some other discussions in various parts of the world, and while such plans are still very tentative, I know that plans for future meetings must be begun very early on. There's no point in starting to organize a conference for next week, because next week there are already 10 different conferences taking place all over the world, including one in Sweden, which is going to attract a lot of people. So what we have been thinking about, subject to funding and all of those various things, is that we might try to organize a second international workshop in Hamilton, New Zealand, as a satellite to the International Biometrics Conference. My friend Harold Henderson is very much involved with the latter conference, but maybe we can work something out so that he will not be completely overwhelmed with such a workshop. I told him it would be a very small workshop, so we didn't have very much work to do. And then I don't always want to push the work to other countries like Finland and New Zealand. I would then propose that the third international workshop be held in Montreal, in either the République indépendante du Québec or in the independent country of Canada. in March of 1995. So that's what we've been talking about. I would welcome further input. I'm sure the anonymous workshop secretary would also want to get further input, and I would like to say to the anonymous workshop secretary, if I can do it simultaneously, that if they want to organize the fourth of a series of Tampere meetings, obviously with a slightly different title since it's been a different title each time, I will require no persuasion whatsoever. We're delighted to come back to Tampere, and I suspect I'll come back to Tampere anyway. So that's still by no means precluded. So, having said all of that stuff, I will now tell you a little bit about canonical correlations in the three-way layout. This is joint work with my student, Julie Bérubé, who is in the audience and has been with me all week, and I guess for most of the last 2 or 3 weeks, and who presented some very much connected material at the matrix tricks section yesterday evening. The work builds on research work which I first reported here in Tampere in 1983 at the first International Tampere Seminar on linear models and their applications, in joint work with Dominique Latour, and in a paper myself on Schur complements and linear statistical models, which was published in the proceedings, copies of which are still available on the desk. That was the two-way layout. I moved ahead to the three-way layout in Auckland, New Zealand, when I was on sabbatical there, and that's published in the volume that should recall the proceedings of the Pacific Statistical Congress, but is in fact just called the Pacific Statistical Congress. So that's the three-way layout, and there's an obscure reference 18 in that paper to more about canonical correlations in the three-way layout. Either that, or it's canonical correlations in the four-way layout, but I don't know how to do the four-way layout, so I'm doing more on the three-way layout. Now let me take these out of there. The three-way layout, as Julie described it yesterday evening, and I'm sure it's been described in many of the talks, concerns a yield, often measured as Yijkl, corresponding to a treatment of variety K, run on experimental unit L, set up in a row-column framework, column J and row I. I like to use R and C for the numbers of rows and columns, and I've now fallen to using V for the number of treatments varieties. I used to use T, and I remember once giving this a similar lecture to this, an earlier version, in which I had T there, and at the end, a person from the audience said, well, I enjoyed your talk very much, I didn't understand anything at all, but you use T in two completely different places to mean different things. So I'll show you the T later on. It's V there, but I think of these things as treatments rather than as varieties. The usual model with the three sets of parameters, alpha, beta, and tau, running over the appropriate indexes. These parameters are fixed and unknown, represent effects due to the row, the column, and the treatment, and Nijk is the number of times that the kth treatment is applied. It's possible, of course, that Nijk could be 0, but the numbers of observations in each plot are not assumed to be all equal, and I use this dot notation, which is quite customary, by summing over the appropriate omitted subscript. While some of the Nijks could be 0, the corresponding sums over rows, columns, and treatments or varieties are all assumed to be positive, as is indicated there. This is so that every row and every column contains at least one treatment, and every treatment is applied at least once. I will go relatively quickly so that I can finish in time, and also because this stuff is relatively standard. I'll assume that the error terms epsilon ijkl are random variables, each with being 0, as the usual assumption, though maybe they shouldn't be denoted by epsilon because that's a Greek letter, and these are in fact random variables, but I as yet don't know a better letter to use. The expectation then is just those three additive parameters. I've omitted the grand mean, which I don't need, and there are no interactions. The observations are then assembled in a long vector, and maybe if I use Dr. Pollock's notation I could improve upon this. I don't know, but I don't particularly like this, but I'm going to get rid of it almost immediately, so I'm not going to use it again. What I would like you all to think about is that the model goes three ways according to design matrices x1, x2, and x3 with parameters alpha, beta, and tau. Maybe they should be beta 1, beta 2, and beta 3, because I really would like to stress that there is a kind of interchangeability. I don't necessarily need that x1 be the rows or x2 be the columns. I will be interested in the full partition matrix, x double dot x2, x1 double dot x2 double dot x3, partition matrix with R plus C plus V columns, and because each treatment is applied to each observation, appears in precisely one row and one column, the row totals of these three design matrices all sum to the column of ones, and so the matrix X is rank deficient with nullity at least 2, or rank at most the number of columns minus 2. If you take those design matrices x1, x2, and x3, transpose them and multiply them by the data vector y, you get correspondingly the row totals, the column totals, and the treatment totals of the original yields. The incidence matrix n1, 2 is formed by the ordinary product x1 prime x2, multiplying the transpose of the appropriate design matrix by the second one. And of course you can get n1, 3 equal to x prime 1, 3, and so on. I said that things were essentially interchangeable. When, however, that is not the case, when the rows and columns are intended to eliminate any possibly undesirable variation in the two directions, represented here by the rows and columns, if you like, the blocks, then it seems that the three-way layout is usually called a two-way elimination of heterogeneity design, which I've always found terribly difficult to pronounce, but nobody seems to have produced an acronym for that, and I guess the letters don't lend themselves to that. I prefer the term three-way layout anyway, and I would like to keep the possible interchangeability of rows, columns, and treatments throughout. So the interest in this talk is not going to focus primarily on the treatment effects, though obviously one could consider it that way. The so-called row-column design, also known as a row and column design, is the setup when the incidence matrix n1, 2 has every component equal to 1. And that's a very common assumption, and row-column designs have been studied widely, but I'm not even going to suppose that that is the situation here, though in some examples that certainly will be so. In some future formulas, it's convenient to remove the RCV notation for rows, columns, and treatments, and I propose to use D1, D2, and D3 for the corresponding dimensions of the appropriate tiers or factors and the numbers of columns in the appropriate design matrices x1, x2, and x3. Again, I want to stress that I can interchange things in any way. So now I guess I'd like to, and I'll put it over here because this is what the talk is all about. I'm interested in canonical correlations of 4 different types, and it will turn out that there are 15 of these altogether, respectively 3, 3, 6, and 3. The original canonical correlations of type 1 were those that Dominique Latour and I considered in Tampere in 83, and types 2 and 4 I considered in the paper presented in Auckland in 1985. Type 3 appears not to have been studied before and was suggested to me for study by my colleague at McGill, Keith Worsley. And there is a related paper that's, I believe, going to appear in the GenStat newsletter by Worsley, Styan, and Bérubé that considers these canonical correlations as set up here, but with a different emphasis. So I'll leave those up here, up there, and continue over here. That's really what the talk is all about, and you'll see some numbers, I believe, quite shortly. The Penrose inverse, of course, is x plus. It's the usual notation. Q sub x is the orthogonal projector on the null space of x prime. The orthocomplement C per x. The index h for all of these canonical correlations in my setup goes up to a number m, so as to indicate only the positive canonical correlations. The multiplicity of the zero canonical correlations is not well defined, can be defined in several ways, and so for the time being I'm going to ignore those, though I will come back to those in a moment. As I said, there are 15 kinds of these of the 4 types. So if you like words better than symbols, this is what the 4 types are. In type 1, we ignore the third tier, or the factor k. In type 2, we augment or somehow juxtapose the factors j and k, putting them together in that partition matrix form. In type 3, we adjust for the second factor, and in type 4, we adjust for them both by the usual kind of adjustment, such as, I guess, may not have been introduced by Chakrabarty, but was certainly studied by Chakrabarty. Going to make the usual white noise assumption that the error terms are all uncorrelated and homoscedastic with the same unknown common variance, and then it is straightforward to show that these non-zero or positive canonical correlations are the square roots of the positive eigenvalues or characteristic roots of the product of 2 projectors. These projectors are each n by n, so there are really n eigenvalues there, and there are going to be a lot of zeros which are of no interest. But it's very convenient to use this notation for theoretical purposes, though I would probably not recommend this for a computer. The canonical correlations of type 2 then are similar square roots of eigenvalues, but where the second matrix now is the augmented matrix based on the projector or hat matrix based on xj and xk. When you adjust, then you get j given k, where you take the hat matrix or projector based on the adjusted qkxj. A straightforward terminology, which is, I think, quite well known. Here comes my definition of T, the number of non-zero canonical correlations that are strictly less than 1. So these are those in the open interval from 0 to 1. I call that T because I like to use U for the number equal to 1, the unit measure if you like. And I've been using M equal to U plus T for so many years now that the associated tables, which you will see, became called MUT tables. And if I change those letters, then I won't have that nice word MUT, so I decided to keep M, U, and T in this context. If you add them up, you get this M, the number of non-zero canonical correlations, which is in turn the rank of the incidence matrix. The three-way layout is said to be orthogonal whenever T is equal to 0. This, of course, will depend on the particular kind of canonical correlation defined. This is considered by Khatri and Shah to be weak orthogonality. If you impose connectedness, then you get strict orthogonality. And I think that in that same paper by Khatri and Shah, 1986, first special issue of LAA on statistics, they used the term, if not exactly, degree of non-orthogonality for the quantity T. It's probably slightly different terminology, but very, very similar context. we need to be more specific, and I'll stick some subscripts on these things. Mi.j then is the rank of the incidence matrix xi prime xj. Ui.j is the number of unit canonical correlations, and if there's just one, then the factors I and j are said to be connected. The maximum, of course, for the rank of xi prime xj is the minimum of di and dj, but I'm going to be interested in that quantity di, so I've used that weaker inequality there, just that this rank mi.j is less than or equal to di. Well, when I was in New Zealand, Chris Triggs introduced me to the James and Wilkinson paper and to canonical efficiency factors, which I guess are almost always called phi, and turns out that these have a very close connection with the canonical correlations. I don't think that James and Wilkinson thought of 15 different types of canonical efficiency factors, as I will show you, but in the excellent book by Nye John, an earlier book by Clifford Pierce, these are discussed in some detail, and those two references really are very good on this subject. Unlike the definition in Nye John's book, and I guess also the definition in Clifford Pierce's book, I'm going to define the nth largest canonical efficiency factor as either being 1 or 1 minus the square of one of my canonical correlations. So if I take the first kind, the I.j kind, then I'm going to take all of those canonical correlations that lie in the open interval from 0 to 1, which have multiplicity t, and then there are a bunch of those that were 0, which until recently I always threw away and ignored. That is, the canonical correlations were 0. Well, if you take 1 minus 0, you get 1. And it seems, if I read the literature correctly, that these ones are required. And it is 6 minutes to go. It is unfortunate, I guess, that the dimensionality zi.j depends on di. That is, it's not symmetric. There's a zi.j and a zj.r. And they will only be equal if those two dimensionalities are in themselves equal. Now, I'm going to go a little bit more quickly. Maybe Eugene will give me 1 minute. The average efficiency factor is defined as the harmonic mean of these canonical efficiency factors, and may be written like this. This is on page 27 of Nye John's book, and would appear then to be bounded below by 0 strictly. And I have asked a couple of people as to what happens when d is equal to u. It seems that the average efficiency factor then is not defined or is equal to 0. I finessed the problem by assuming that d, the dimensionality of that factor, is bigger than u. Efficiency factor will be equal to 1 if and only if the factors are 0. I shall skip the verbiage on that one and announce that I have moved ahead from MUT tables of 1985 to MUTC tables of 1990. The example of this row column design was presented by Peter Armitage at the beginning of the Pacific Statistical Congress in Auckland in 1985, but not published in the book Pacific Statistical Congress. But it's a nice sort of balanced kind of layout in that there are relatively few non-zero canonical correlations and efficiency factors, and you can see the z's, the phi's, the rho squares, the e's, and there's an e prime. That e prime is the corresponding version of the average canonical efficiency factor when you switch these subscripts. Now, 2 more minutes or something like that. I'll announce Theorem I, which I am hoping is new. I claim that provided the degree of non-orthogonality of the layout associated with I dot jk, if that is at least as large, if not larger than the degree of non-orthogonality of the two sub-designs, where G is either J or K, then I claim that the canonical efficiency factor average, the harmonic mean, associated with I dot jk is less than or equal to the minimum of the corresponding average factors for the two sub-designs. Claim that there is equality there if and only if these canonical correlations are equal for all of the index h running up to m, and then of course the m's are equal and the u's are equal and the t's are equal. The motivation for this theorem is Theorem I of Shah and Eccleston, who treated row-column designs. That assumption appears not to be needed at all. They also assumed that the designs were treatment connected, but as this little proof shows, this, I think, is a much stronger condition, a much weaker condition, and of course, this implies this. I want to say only one other thing, then I will stop, and that is that a sufficient condition for equality is that these canonical correlations be equal. According to what I wrote here, a sufficient condition for this is that I dot j having adjusted for I dot k having adjusted for j be 0. Where am I? Sorry. A sufficient condition for equality is that those canonical correlations be equal. A sufficient condition for equality of the two average efficiency factors is that these sets of canonical correlations be equal. A sufficient condition for that is that I dot k, I and k, having adjusted for j, be orthogonal. I think that that is also necessary. I thought I had proved it a couple of hours ago, but I will need to sleep on it and make sure that it is okay. But it seems to me that it's necessary and sufficient that mi dot k given j be equal to 0. A sufficient condition for that was announced, I think, in the Pacific paper, is that you have strong orthogonality or weak orthogonality and connectedness of the two sub-designs, and of course you will have that for one of them if it is a row-column design. So you would need two row-column designs, or one would have to be a multiple of a row-column design, and that is what the Armitage example exhibits. Okay. I have more, but I am out of time. Thank you very much.
Thank you very much, George. Any big comments or questions to George?
Yes, Kirti.
George asked me to ask a question. So my question is, I have some difficulty with the concept of efficiency factor for a disconnected design. I think it's a very nice extension that we have there. So I would appreciate some comment on the relevance of efficiency factor for a disconnected design.
I guess I don't know the answer to that. I find it interesting algebraically, and I noticed in several of the talks at this workshop that people were now considering disconnected designs, and I think I heard comments along the lines that you have just made. Well, why do you do that? Because you can always split it into the several pieces.
Not like the column designs you can't split, not necessarily.
Aha.
That's why.
I thought there was a result in Searle's book that maybe it's just for the two layer.
That's why the extension is very important, because the design is not naturally split, and you do not know whether the column design is disconnected unless you compute the rank of the C matrix. We'll talk more about that.
Yeah. Oh, certainly. I'm sorry you're going so far away in the very near future, because certainly I would like to talk to you more about it, and it's a shame since we do live in the same country, at least at the moment.
Anything else? One further question? Okay. Oh, there is one.
Just, I just want to know some application of, you see, when data is collected from any three-factor so then this kind of unbalance could arise, and then I think whatever we are doing will become very relevant. And I am aware of the fact that a lot of situations where data is collected are unbalanced and so on. Particularly, you see, since I was going into statistics from my childhood, as I saw, people do not worry about how to produce data. They worry that the statisticians have addressed themselves to is how to analyze data. And as I said to Professor John Pukkila once in New Hampshire in '72, you see, the less we worry about statistical design, the more jobs we create by statisticians. See, there is an inherent danger in doing too much of design. the inherent danger is that if you do design properly, then say data will be balanced, there will be a lot of optimality, and it will be easier to do statistical inference. And so, you see, problems will get solved easily, and so if there are many statisticians, they won't have enough jobs.
Well, all I can say is that the best laid plans of mice and men don't always work out that way, and one's flowers may not always bloom, and one's food in the fridge may not always be edible when you open the fridge door. So you don't know, even if you've designed the experiment, that you might not have an empty cell. And you don't know, in particular what Kurti Shah was just saying, that the pattern of empty cells might be such that the thing becomes disconnected in a non-obvious way, particularly with larger layouts such as... I know, no, I'm just saying that this happens. But I think we should stop, because otherwise I shall get into big trouble.
George, thank you very much for the presentation.